Today we're going to discuss the proof of the inverse function theorem. So the statement is as follows. Let f be a differentiable map from Rn to Rn, and assume that the derivative of f at some point p0 is invertible. Then f itself is actually invertible. So there's a neighborhood u of p0 and a neighborhood v of q0, and f from u to v is 1 to 1 and onto, and its inverse, which is now defined because it's 1 to 1 and onto, is also differentiable. So how are we going to prove this? The first step is to reduce to a simpler case. So we can compose f with translations. Oh, sorry. So when I wrote q0 here, I should have written f of p0. We can compose f with translations so that both p0 and f of p0 are equal to 0. And this is okay because we're not going to be changing anything really. Our neighborhoods u and v will also translate and remain neighborhoods. F will remain 1 to 1 and onto, and the derivative of f will not change because the translations have derivative the identity. We also want to compose f with the map df at 0 inverse. So now assuming we've done the first composition, this means will mean that we can assume df at 0 is the identity. So this simplifies our life by a lot, and the reason why we can do this is, again, the chain rule. Essentially, nothing will really change. We're just doing a change of coordinates. And because df at 0 is invertible and non-singular, we're basically just changing coordinates on the domain and range. Okay, so now let's set up our proof. So by step 1, we can assume that f at any point u is, f at any point v, f at u is just equal to u plus r of u, where r of u is some function such that r of 0 is equal to 0, and dr at 0 is also the 0 transformation. And our goal is for any v near 0. So v being near 0 corresponds under all of these simplifications of step 1 to v being in this neighborhood u of p0. Sorry, v being in this neighborhood v of f of p0. So our goal is for any such v to solve the equation f of u equals v for some u. And let's rewrite this now because we have our simplification of f. So this is equivalent to saying that u plus r of u is equal to v. And that's the same thing as saying that u is equal to v minus r of u. So we're going to give the right-hand side a name. We're going to define the function tv of u to equal v minus r of u. And this is something we're going to be using heavily throughout the proof. Because if tv of u is equal to u, then v minus r of u is equal to u, and v equals u plus r of u, which is f of u, which is what we wanted all along. So the claim that we're going to prove, and then that will then prove the theorem, is tv has a unique fixed point. So now, because it's a unique and exists, it depends on v. So I'm going to call it k of v. This is now a function from v to the fixed point of tv, where dk at 0 is the identity, which is equivalent to saying that k of v is equal to v plus little r of v, where r of v is some function that is little o of the absolute value of v. So if you haven't seen little o notation, just know that we say that two functions we say that f is little o of g if the limit as x approaches 0 of f of x over g of x is equal to 0. And I mean, you can set this up for any limit approaching any number, but essentially this tells you that that k of v is very close to v, except for maybe some small error that disappears as v gets really small. And so why can we prove the theorem from the claim? So the proof of the theorem assuming claim. Okay, so if the claim is true, then we just set f inverse of v to equal k of v, and we're done. This gives us our inverse. And we also wanted to show that k is differentiable. Well, okay, so to do this, we want to show that its derivative exists. So we'll show that dk at v is equal to the inverse of df at k of v, which is what we want for k to be the inverse of f. And in general, if f is more differentiable, say f is twice differentiable or infinitely many times differentiable, we can just use induction to show that k also is as differentiable as f is. So the final thing that we're going to show in this video, we're going to prove the claim in the next video, is that k is differentiable. So the fact that f of v is defined, we just need to show that k is differentiable. So notice that df at a point u is equal to I plus dr at u. So, and also notice that k of v, so because k is a fixed point, k of v is a fixed point of tv, then k of v is equal to tv of k of v, which is equal to v minus r of k of v. So now I can replace this left-hand side with v plus r of v, because I know that k of v is equal to v plus r of v. And I can remove the v's, and I get that r of v is equal to minus r of k of v. And so this tells me that when I take differentials, dr of v is equal to minus dr composed with k of v. So I can plug this back in to the df equation, and I get df at u is equal to I minus dr. So if I apply df at the point k of v, then this should be I minus d little r at v. And so then if I multiply dk at v by df at k of v, I get I plus d little r at v times I minus d little r at v. And this is just I minus d little r at v all squared. So my goal was to show that dk of v times df at k of v was actually just the identity. So what I want is that dr at v is actually just 0. So what I know is that dr at 0 is equal to 0. This comes again because r of v is little o of v. And I can actually repeat because the fact that df at 0 is invertible is an open condition. I can repeat my step 1 argument within the open set where df is non-zero or non-singular to show that d k of v df at k of v is equal to the identity for v where df is non-singular. So actually I get that dk is equal to the inverse of df at k of v. Okay, so now what we've done is we've proved the theorem assuming the claim. So we've proved this, and now we've proved the whole theorem assuming the claim. So what we're going to do next time in the next video is prove this claim.